Hey everyone, welcome to the lecture for 8.3. So we're going to be doing confidence intervals for population proportions. So in the past, we have been trying to get a good estimate or a good guess for population means. And the way that we did that is we took our population and kind of transferred it or translated it perhaps into a sampling distribution. So that was 7.1 and the central limit theorem. Then in 8.1 and 8.2, we looked at the various ways we could use a sample from the population with using the sampling distribution for the population to construct a confidence interval that would give us an idea of where the true population mean was. So we're going to be doing very much the same thing, except that instead of looking at a population mean, we're going to be looking at a population proportion. So we're going to construct the confidence interval kind of starting off where we're going to consider our population to be a binomial distribution. And remember that the mean for a binomial distribution is determined by n and p. So x, the random variable, counts the number of successes. And so if we say that x follows a binomial distribution with n and p, then we know that the population mean is NP, and the population standard deviation is the square root of NPQ. We could also write this as the square root of n times p times 1 minus p, since q is just the complement of p, 1 minus p. So as before, when we wanted to go from a population into a sampling distribution, we kind of have to figure out how we're going to transform our mean and our standard deviation from the population. So for us, we know our mean is NP, we know our standard deviation is root NPQ. To take a kind of metric on a population and convert it into a proportion, all we're going to do is we're just going to take x and divide it by n, right? So consider if we have a class of 30 people, maybe that's my population, or maybe it's my sample. Regardless, just a group of people, let's say 30 people in a class, and I want to know what proportion of that class went to tutoring at the tutoring center last week. And so let's say x was 5. So my random variable x is counting the number of students who attended the tutoring session last week or went to the tutoring center. And it's very easy for me to convert that into a proportion. I would just say, okay, 5 out of the 30 students. So you see here, we have this idea of x over n, the number of successes, if you will, the number of times people went to the tutoring, and then n is the total number of trials or the total number of people in my sample. And so if I do this division by n, you'll notice that what happens is, right, so here you have a population, and here we're going to have our sampling distribution. Well, if mu equals NP, then for our sample, why don't I just take NP and divide it by n? And if sigma was NPQ, why don't I just take the sigma for the sampling distribution to be the square root of NPQ over n? And this is exactly what we're going to do. So if we look at mu and sigma for our sampling distribution, I can cancel out an n with mu and I'll have just p by itself. And if we take and simplify sigma over here, there's a little bit of a trick to it, but nothing too fancy. We'd end up with the square root of PQ over n. And so that is precisely how we get this new random variable p hat. So p hat is defined to be x over n. This is the estimated proportion, and we have p hat actually follows a normal distribution where the mean is P and the standard deviation is the square root of PQ over N. So notice that's exactly what we got here when we divided our mu and our sigma by N. So now that we have an idea of what the theory is behind what we're doing, we want to go ahead and compute a confidence interval for a proportion. And the way that we're going to do that is very, very similar to what we did in 8.2 and 8.1. So we're going to start with our point estimate, which is little p hat. So notice that in red, our random variable is capital P hat. And so we use capital letters for random variables and we use lowercase letters for actual like data values. So here we have our point estimate is lowercase p hat equals lowercase x over n. So x is going to be the number of successes from our sample data. N is going to be our sample size. And p hat is going to be the proportion of our sample that, answered yes to some question or in some way measures the proportion of success. The next step is to find the z-score. And so the z-score, again, because p hat, capital P hat is normally distributed, normal distributions are associated with a z-score. Whereas in 8.2, we didn't quite have a normal distribution. We had a t-distribution, and those are associated with t-scores. All right, so we're normal. We have a z-score. We know how to compute the z-score just by the confidence level, and we have Excel to do that for us. And we also need to find the error bound, right? That's going to be our z-score from the second step, multiplied with our standard error. So remember that standard error is really just the standard deviation of the sampling distribution. And so for us, we saw that our sample distribution had a standard deviation of the square root PQ over N. So here we have P hat Q hat over N. But again, this is really just because P hat is the proportion or point estimate from the sample itself, right? So this is kind of the difference between X and X bar. Q hat, of course, is just going to be 1 minus P hat. And once we have our standard error and our critical Z value, the product of those two is how we construct our error bound for the probability. So once we have our error bound for the probability, the EPB, we can subtract that from our point estimate to get our lower bound for the confidence interval, and then subsequently add that to our point estimate to get the upper bound for our confidence interval. And so structurally, when you're looking at what a confidence interval means, it follows the same structure as when we did this for populations where the standard deviation was known and we were computing the mean, i.e. it is the same as 8.1. So you can see that in the middle blue shaded area, that's where we're going to have however much confidence, right? So if this is a 95% confidence interval, then that blue shaded area has 0.95 as its value. And then the alpha over 2, that's just the leftovers. If we have a 95% confidence interval, we know that 5% is left over. So you'd have 2.5% on each side. If we had, say, a 90% confidence interval, well, then 10% would be left over, which is 5% on each side. And so that's just the general structure of how the confidence interval is constructed. So let's go ahead and work on a few examples just to get you familiar with how these problems are done and how you're going to use Excel to solve them. So the first thing you're going to want to do when you go to Excel, make sure that you're on the right section. So we need to be in the 8.3 tab. And you'll know it because it's going to have a bunch of P hats everywhere. And also the top of the screen in Excel will tell you what section you're in. All right, so In the first problem on the left side of your screen, you'll see if n equals 250 and p hat equals 0.61, find the margin of error at a 99% confidence level. So all we're going to do is just plug in the values that were given. So I have 250. We know that p hat is 0.61. And we have a confidence level of 0.99. So now we can come down towards the bottom of our table and we see EPB margin of error. So this is error bound for the proportion. Previously we had EBM, that was error bound for the mean. They're both the margin of error for their respective cases. And we see that the margin of error is 0.0795. In the next question, we're asked about polls. In a recent poll, 210 people were asked if they liked dogs, and 49% said they did. Find the margin of error of this poll at the 99% confidence level. So we want to take N, our sample size is 210. Our p hat is the percentage of people that said they like dogs. So this is kind of like your estimation of success, if you will. So this is 0.49. And then we have a 99% confidence level. And so again, we're just going to grab the margin of error, which we see is 0.0889. In the third example, it's a little bit different because we have so far been given p hat as a decimal. In this case, we aren't given p hat explicitly. We're told that 500 people were sampled, and of that 500 people sampled, 135 had kids. So we have to figure out what is p hat from this. Well, p hat is just going to be the proportion from the sample that have kids. So the proportion is just going to be 135 over 500. And you can type that straight into Excel. So just 135 / 500. And that will tell Excel to go ahead and compute a division here. So I get 0.27. Our sample size was 500, right? Because we asked 500 people. And then we want to construct a confidence level with 99%. So here we're asked for the confidence interval, not for the margin of error as we were previously. So we want the confidence interval. So coming all the way down to the bottom, I see it's 0.2189 and 0.3211. So what that means is that we're 99% confident that the true population proportion for people who have kids is between 21.89% and 32.11%. All right, so let's try this again. Assume that a sample is used to estimate a population proportion P. Find the 90% confidence interval for a sample of 255 with 214 successes. Enter your answer as a trilinear inequality, blah, blah, blah. Okay, that's like a mom issue. I just am asked to get the confidence interval. So again, I'm not given p hat explicitly, but I am given that 255 people were asked, 214 said yes. So as a proportion, that's 214 divided by 255. My sample size is 255. And my confidence level is 90%. So I can see here that my confidence interval is from 0.8014 to 0.8771. All right, so now we're going to transition into a little bit of a different type of problem. So here, a political candidate has asked to conduct a poll to determine what percentage of people support her. If the candidate only wants a 9% margin of error at the 90% confidence level, what sample size is needed? So if we wanted to compute our confidence interval, margin of error, or critical Z value, that's all done here in this first part, right? And we have to give it p hat, we have to give it n and a confidence level. But we have two other places to kind of play in on this sheet. One of them is computing the error bound for the population from a confidence interval. And the other is going to calculate the sample size n. And so here we're asked what size of sample is needed. So that's exactly what I want to use. I want to use our sample size calculator. So in order to do that, I need to have a point estimate. I need to have my margin of error. I need to have my confidence level. And so I can see right off the bat that I already have two of these. So my error bound, or my margin of error, is 0.09, right? 9%. My confidence level is 90%, so 0.90. But I don't have my point estimate. And so there's a bit of a trick for this one. If you don't have a point estimate given to you, that's either going to be explicitly as a decimal, or if they give you, say, X amount of people out of this many people, something that you could compute a point estimate for. If you have neither of those, the key is to just let this equal 0.5. The reason you do that is because 0.5 is the value which will make n the largest. And the reason you want to have n be as large as possible is because we don't know what p hat is. However, if we use the value of p hat, that's going to make n as big as possible, then this value of n will work to ensure that we achieve these margins of error and this level of confidence with any sample, with any proportion. So here we see that we calculate the sample size n and we get 84. In the next question, we intend to estimate a population proportion with a confidence interval. The data suggests that the normal distribution is a reasonable approximation for the binomial distribution in this case. While it is an uncommon confidence level, find the critical value that corresponds to a confidence level of 80.5. And so this has like some actually quite deep theory in it. However, the first part, the data suggests that the normal distribution is a reasonable approximation for the binomial. This has to do with how large your sample is and what your value of p is and kind of how those interplay together. For this course, we're not going to worry about that. We're just going to kind of take it on faith and going to find this critical value that corresponds to a confidence level of 80.5%. So in order to do that, all we need to do is just tell Excel what our confidence level is. So z-scores only depend on the confidence level. That's it, nothing else. So if you know your confidence level and you know that you can use a normal distribution for your confidence interval, then you just go ahead and compute your z-score by inputting whatever you get for your CL. So here we see that with nothing else given, just the confidence level, it gives us our alpha, which is the area outside kind of in the tails and the wings. They are called tails, by the way. And then Z alpha is the z-score associated to those areas. So all we're going to do is we're just going to grab this. And so I have my critical Z value, and I'm all done with this problem. All right, the last example that we're going to do is we're going to take a confidence interval given, and we're going to convert it into the form p hat plus ME. So remember that ME stands for margin of error. So in this third box on the bottom left of Excel, we have a way to compute the EVP, the error bound for the proportion, and p hat from the confidence interval. So I just need to input my lower bound, so 36.8, and my upper bound, which was 45.6, and it's going to go ahead and compute my sample proportion, my p hat, and it's going to give me my error bound for the proportion, aka my margin of error. And so some of you may already be thinking, wait, why did we just use like the actual straight percentage format? Like, don't we have to convert this into a decimal? And as far as this problem is concerned, you can do it either way. So when you're using your confidence level, you need to convert it into a decimal, because the way that Excel, the way that your computer, the way that a Z table, whatever you're using, the way that they determine what your Z value is they look at the area under the curve. And we all know that for probability distributions, the area under the curve, one, represents probability, therefore is between the values 0 and 1, and 2, the sum of it has to be equal to 1. So that's why you have to have a decimal between 0 and 1. For computing the error bound for the proportion and p hat from the confidence interval, I'm just saying, what's the middle of this confidence interval? Okay, it's 41.2. And then how far left and how far right am I going? Okay, it was 4.4. So there's no conflict in whether I give it a percentage or a decimal. So if I had wanted to give it a decimal, you'll see that we end up getting not that, sorry, let's try something with an equal sign. There we are. We're going to end up getting the same thing, just in decimal form. So we can see that in this case, we got 0.412, which is the same as 41.2%. Right, so this is going to be as a percent. The first one is a percent. And the second one is a decimal. So that's everything that you need to know to complete the homework for 8.3. There's a very rich theory here. However, we're focusing on just constructing the confidence intervals. So I would definitely encourage you to read about the theory on your own and make sure to master the art of constructing your confidence intervals.